All right, y'all. So, welcome to our first asynchronous lesson for the quarter. So, you can see that our learning targets for today are to solidify our understanding of the Pythagorean Theorem, to apply the Pythagorean Theorem in order to construct something that we call a special triangle. We'll see what that looks like in a little bit. And we're going to recap some topics about circular measurement and kind of the connection between triangles and circles. So, let's get ourselves on started. So to start things off, I figured we could do our quick Pythagorean theorem recap together just one more time. And what I'm going to do is I'm going to go over those questions from the exit ticket that we had in our first day of class. So here I have a triangle, a right triangle. Mind you, I should give this guy a right angle. And this right triangle has side lengths 8 centimeters and 11 centimeters on the legs, and it has an unknown hypotenuse. Now, remember, Pythagorean theorem tells us that the legs of a right triangle, right, those are the ones that create the right angle right here, A and B. If I square them and I add them, it should equal the hypotenuse squared, that long side across from the right angle, right? So that means that basically 8 here is one leg, that's A. 11 here is B, it's the other leg. And so 8 squared plus 11 squared should equal this unknown value, which let's call it c squared. And it's pretty simple, right? 8 squared is 64, 11 squared is 121. If I add those, I get 185. So c squared is equal to 185, right? So if c squared equals 185, then c would be equal to the square root of 185. Now, I'm actually going to just leave it in that form. You could evaluate this as a decimal, but personally, I kind of actually really find it beneficial to keep things in terms of a square root when you're working with side lengths, at least unless that square root it's beneficial to leave things in a square root if you cannot simplify the square root, right? Like if I had the square root of 81, right, square root 81, of course I'm going to write that as 9. In fact, even if I have the square root of 8, what I'm going to do is I'm going to recognize that the square root of 8 is the square root of 4 times 2, right, because 8 is 4 times 2. And 4 is a perfect square, right? So essentially what I'm doing is I'm recognizing that 8, right, the number inside my square root, has a factor, which is a perfect square. So I should be able to pull it out, and the square root of 4 is 2. So this gives me actually 2 square root 2. This is the proper way to deal with square roots, aka rationals. Essentially, you take any factors which are perfect squares out, and you square root those, and you leave the rest of the stuff inside, right? All right, so however, 185, I believe, does not have any factors which can be pulled out that are perfect squares. So we're going to leave it in that form. All right, let's try this other one. Now this one's mixed up because instead of the hypotenuse being unknown, it is one of the legs that's unknown. I'm going to give it another right angle just because I think that I missed that when I made this question. Should have given it a right angle when I made it. So we know that the side lengths squared and added, so this question mark, we'll call it A. So A squared plus 20 squared should equal the hypotenuse squared, which is 25. So A plus 20 squared equals 25 squared. Well, 20 squared is 400, and 25 squared is 625. So therefore A squared plus 400 equals 625. I'm going to subtract 400 from both sides, right, and just solve for A. You guys have done these all day before. We know that A squared is equal to 625 minus 400 is 225, and we square root it. The square root of 225 is actually a perfect square. This is 15 squared. So A should equal 15. So I'm going to put that there. So I hope this was an easy little recap about Pythagorean theorem. Something that's, I think these were okay examples, but one issue is that like they're kind of in the perfect same format, But like, if you guys think about it, like my triangle could be actually a rotated triangle. For example, like I could have a right triangle in this form where the right angle is up here. And then now that changes my perspective. This is A, that's B, this is C, right? C is just always going to be the one across, directly across from the right angle, right? All right, so now what we're going to do is we're going to go ahead and take a look at how using Pythagorean theorem in order to construct something that we call a special triangle. Engineer, I need a diagonal walking path to cut through the square plaza downtown. I want you to design and draw up the plans for this path with accurate measurements and angles for my construction workers to follow. I myself cannot be bothered with such trivial maths. You got it, Chief. Ah, crap. I forgot to ask him for the measurements of the square plaza. Well, I'm sure I'll figure something out. Alright, y'all. Well, I guess the commissioner has asked us to construct this diagonal footpath that goes across some square plaza downtown. So let's at least start off by drawing ourselves a picture of this. So I've got some square plaza, so I'm just going to give myself a big square to work with. I think that's square. Let's hope that's square. Yeah, that's looking kind of squarey. And what we know is that the path is supposed to go diagonal. So I'm going to take the green and I'm going to draw a big diagonal path going across here. And now, as I said earlier, I forgot to ask him how big the dimensions of the plaza were. But I think I can work with this. Because I know that it's a square. So what I'll just do is, if I don't know the dimension, I'll use something to represent the length of the square. And I'll just work with it from there. What could I use to represent the length of a square? Oh, maybe the variable x, for example. I could have used L, but I like x. And because this is a square and all sides of a square are equal, I know that the other side is also x, right? So that's fair. I know two measurements of my sort of drawing here. I also know that this guy would be x and this guy would be x, right? Some other things I know, squares have right angles. So this is a right angle here. This would be a right angle here. And this guy is cutting it diagonally in half. If I cut, because this is normally supposed to be a right angle, right? If I cut that right angle in half, though, how big would this angle here be? It's actually going to be 45 degrees, right? Because a right angle is 90, if you remember. 90 degrees. And down here, once again, I have a right angle being cut in half. So this is also going to be 45 degrees, right? And I hope you guys see what I see, because I see a little something that's a little bit convenient for us here. But if you don't see what I see, I'm going to help you see what I see. I'm going to erase the stuff that's in the way. All right, so watch this. I'm going to say I don't need to know these side lengths, right? I don't need to know those. Truly, all I need to know is this path, this walking path that I'm designing, right? In fact, I don't even need to know what half of this plaza looks like, because all I care about is that the walking path crosses halfway diagonally across, right? Now, do you see what I have formed here? Maybe you don't, because my drawing is really shit, but it's a triangle, guys. It's a right triangle, okay? It's a right triangle, and it has equal sides. We call this a right isosceles triangle. If anyone knows why I call this a right isosceles triangle, I would love to see. Okay, I'm not gonna be out here asking y'all to post things in the comments of the YouTube videos all the time. However, if anyone happens to know why this is called a right isosceles triangle, I was going to tell y'all, but I think it'd be more fun to see if anyone knows. So why is this shape here a right isosceles triangle? All right, so this right isosceles triangle, which has angles 45, 45, 90, we basically have already constructed all the information about it. All we need to do is figure out this hypotenuse length. And now, I'm not going to actually get a whole number answer for this because my side lengths are in terms of x, but I could get the answer for it in terms of x. I just got to use Pythagorean Theorem. I know that a squared plus b squared equals c squared. So I know that x squared plus x squared should equal that hypotenuse squared. What should we call that? Let's call it c squared. Okay, so we're solving for c in terms of x. That's a common thing in math, by the way, guys. Solving for one variable in terms of another variable. And y'all have done it all the time before, actually. It's what you guys used to do when you would get things in y equals mx plus b form. You were basically solving the y value in terms of x. Same thing here. So x squared plus x squared, that's 2x squared. And that equals c squared. Okay, so if I just want to get c, I should square root both sides, right? So I'm going to square root it. I'm going to square root this. And notice, by the way, y'all, this is something that's really important. I see this all the time. People make this mistake. The square root is impacting the entire left-hand side, including this 2. All right, y'all? So I can't just say that this is equal to 2x, right? Because yes, the square root of x squared is x, but what's the square root of 2? It's the square root of 2, guys. So what you'll notice is that actually I'm gonna end up with the square root of 2 times x. Let me rewrite this because it doesn't look super clean the way I wrote that. So when I square root 2x squared, I get square root of 2 times x. And this is equal to the square root of c squared, which is c. So this hypotenuse there, I'm going to erase my right isosceles triangle. Don't forget. If you know what that means, tell me. And so my hypotenuse here should actually be the square root of 2 times whatever the dimensions of this thing are, right? Remember, the whole reason why I was using x is because I forgot to ask how big the plaza was. But that's fine, because what I can do is I can just show up with these plans, and then later on, once I'm at the plaza, measure this side length, and then I'll just scribble it out and throw in a 10 if it was 10, or 100 if it's 100. 100 what, you might say? Let's say it's meters. All right, let's go back. So the point here, guys, is that I ended up with the square root of 2 times the original side length. This is actually something that's a very common triangle to find, mostly because of these angles here. Do you see that? 45 degrees. This 45 degree is a very important angle for us, right? I mean, it's half of 90. It's pretty common to want half of 90 as an angle. And we call this triangle actually by the name of its angles. We call it a 45, 45, 90 triangle. Or we call it a right isosceles triangle. Now, essentially, this is actually something that might sound familiar to you guys because you should have learned about this type of triangle in geometry. It's called a special triangle, and there's one more special triangle, which I will have y'all solve for in class on Friday. But essentially, guys, this triangle is going to come up very useful for us in the future with our trigonometry class. Essentially, because 45 degrees is such a common angle to need to do work with, this triangle just appears over and over and over, and it's just gonna be something that we're gonna actually use to construct what we call the unit circle. We'll get to that in a future topic, though. So here's a cleaner version of that 45, 45, 90 triangle that we created with x, and square root 2x as its side lengths. But something that might be useful for us is to kind of see what does this triangle look like in different forms, right? Let's get rid of those variables. If you guys remember from geometry, something that's useful about similar triangles, right? Okay, let's take a step back actually. What are similar triangles? Essentially, guys, in geometry, anything that is similar shapes are just two things which have the exact same shape regardless of their size. So you can see that this triangle is getting its lengths doubled to make this one. Let's say this guy is a 3, 4, 5 triangle. This one's doubled, so it's 6, 8, 10, right? So these are similar triangles I've drawn here. What you'll notice, what we'll notice about similar triangles is that all the angles of a similar triangle are congruent. So you can see that the top angle there matches the top angle of the other one. The bottom angle here matches this one, and they're both right triangles. Similarly here, guys, with this triangle here, I can actually scale it. So watch this shit. Let's see if this works. I can't do that. Lol. I tried to move it around. I tried to scale it. But essentially I can make the side lengths bigger or smaller. I could double them, I could triple them, I could quadruple them, or I could even scale it down. I could make it half as big. I could make it 1/3 as big. I could divide all the side lengths by x. If I divide all these side lengths by x, I'll still have a 45, 45, 90 triangle. That's why that triangle is so useful. Because the 45, 45, 90 triangle is defined by its angles, then it essentially tells us a pattern that emerges. X divided x would be 1. X divided x is 1. X divided x cancels out, and I'm left with the square root of 2. And I am left with this guy right here. This is kind of like the base. This is kind of like the base 45, 45, 90 triangle, right? It's got side length 1, 1, square root 2. This might look a lot more familiar from geometry. So the thing with this is that I can actually, because of similar triangles, I can actually scale this guy up and down, and it will allow me to eventually do essentially trigonometry, right? Sine, cosine, tangent, and all sorts of things. Anytime I have a 45-degree angle. So what I want y'all to do is make sure that you have this triangle, 45, 45, 90 triangle, really seared into your mind for now. All right, y'all. So the final thing I kind of wanted to talk about today was a little bit of a recap about circle measure and kind of looking at the connection between circles and triangles. So first of all, what are the important measurements in a circle? One thing that's pretty important in a circle is its radius. So you can see here I have a circle that I kind of plotted on the XY axis just for, because why not, man? Graphs are cool. And so if I have a line going from the center of the circle all the way out to the edge, this is called the radius, right? And what will happen is that the radius is always equal no matter where I go around the circle, whether it's this diagonal, that diagonal, this diagonal, that diagonal, or even these ones that are going horizontal, vertical, horizontal, vertical, right? Every single one of these lines around this kind of wheel looking guy is going to be the same length of, well, I can count how many squares in my graph it took. It was 1, 2, 3, 4, 5, 6. Now you'll have to just, I know that my drawing's not perfect, but since it's supposed to be a circle, we know that every single one of these lines, if this guy's 6 here, then every single one of these should be 6 all the way around. That's a lot of 6s, huh? Very lucky. So I'm going to keep this 6 here and focus on it. So we know the radius. Something else that we know is called circumference. Remember, guys, circumference is the distance that it takes to go all the way around a circle. This is the circumference. Now, we've previously defined circumference. Circumference is equal to 2 pi times the radius. So the circumference of this circle would be 2 pi times 6, which would be 12 pi. You'll notice that pi comes up all the time with circles. It's actually kind of a thing. It's as if pi was derived from circles or something. That'd be too crazy. Now, the last thing that I'm going to kind of show you here is that, check this out. If I take this radius that I drew here and I drop the line on down, what do you see there? You see yourself a triangle. If I drop this radius down, you see a triangle. You see triangles all over. In fact, what you'll notice, guys, is that triangles appear all over my circle. In fact, I could draw even more. I could draw all these radiuses. No matter where I draw a radius, I'm going to get myself a triangle. Draw a radius there, get myself a triangle. This is getting kind of messy, huh? What if I draw my radius vertical, though? That's a kind of shitty triangle. I don't like that triangle. That sounds like a triangle to deal with another time. All right, y'all. So I've cleaned up the circle, left this one radius here so that we can focus on it a little bit closer. Something that I want to point out, guys, in this triangle here, you can see that I actually could have an angle measurement going from the x-axis, the positive x-axis, up to the radius. Now, just for the sake of this example, let's say that I measured this angle and it was 45 degrees. That is very familiar, isn't it? This right here would be one of our 45, 45, 90 triangles. Now, we saw before that our 45, 45, 90 triangle had the measurements which followed some sort of pattern of either of 1 to 1 to square root of 2, right? That's what we saw our 45, 45, 90 triangles tend to follow. This guy here has a radius, which is the hypotenuse, you can see, of 6, though. Now, something that's interesting, guys, is I can actually apply my special triangle to this triangle here within the circle in order to find this side length here. I'm going to call that x, and this side length here, y. Now, why might I want to know these two variables? Because then I could know the exact location of this coordinate here on the circle. It would be x comma y. You see that? X comma y. This has all sorts of reasons why we might want to know these values, right? For physics, applications in cyclic behavior and harmonic motion, right? All sorts of times when things move in a circle, right? And it's just useful to know kind of, okay, well, what if I'm not on, here where it's 6 comma 0, so I could know actually where that point is, or, oh, I know right here is 0 comma 6. What about in the middle? How do I determine that? This is where trigonometry is going to come in handy, y'all. And this is where we're going to actually find this xy value using ratios. So let's check it out, right? Because remember, guys, similar triangles, their side lengths are supposed to be proportional. Proportional implies that there is some ratio happening between this triangle and this one. In order to determine the triangle ratio, all you have to do, guys, is compare two of the corresponding side lengths. Namely, I have square root of 2 and I have 6. So I know that for every square root 2 that this triangle has, for every square root 2, this is how you write ratios, by the way. You use a colon. So for every root 2, you have 6 on the big triangle. So in order to turn that into a ratio in terms of 1 to something, all I got to do is divide by square root of 2. You see that? Now, this value here, 6 over root 2, most math classes and most math people will actually do what they call rationalize the denominator. Basically, they don't like to have square roots in the bottom of fractions. It's just kind of unkosher. So what we're going to do to deal with that, guys, to get rid of this square root in the bottom, we're going to just multiply the top and bottom of this fraction by square root 2. Right? Because what's going to happen is on the bottom, square root 2 times square root 2 is just 2. And on top, the square root will appear. Why am I allowed to do that? Notice, by the way, guys, that square root 2 divides square root 2. This is equal to 1. So did I actually change the value of 6 over root 2? I didn't. I multiplied it by 1. I simply changed its form. So that's kind of a side note about what we call rationalizing denominators within our side note about ratios. That's funny. So guys, what we see is that essentially the ratio from my normal, my standard 45, 45, 90 triangle to my one here in this example is 1 to 6 root 2 over 2. Now I could evaluate that with a calculator, but I'm going to leave it in this form because I like square roots. And what I see here, guys, is that if for every 1 unit long my 45, 45, 90 triangle is, this guy here is 6 root 2 over 2 units. So that means that x is equal to 6 root 2 over 2, and y is equal to 6 root 2 over 2. So I have actually been able to apply my similar triangles with my 45, 45, 90 with this kind of radius here at a 45-degree angle within the circle in order to determine the coordinates of this point right here. So I know that that point is at 6 root 2 over 2, comma 6 root 2 over 2 for y. All right, y'all. So just in conclusion, to recap, what did we learn today? We have solidified our understanding of Pythagorean Theorem. Hopefully, we should be able to use Pythagorean Theorem to solve for missing side lengths on any right triangle. We additionally applied the Pythagorean Theorem to construct a special triangle. That triangle was the 45, 45, 90 triangle. And we also recapped some things about circular measurement. In fact, not only did we do that, we did tons of other things. We learned about simplifying square roots. We learned about similar triangles. We learned about ratios. And we learned about how to rationalize a denominator. In fact, we even saw a little bit of using trigonometry to determine location of a coordinate on a circular motion, on a circular path. That's a lot of stuff that we learned, and I hope that you guys found that you learned something interesting today.